Ladies and gentlemen, welcome back to lesson 20 in group theory. In this lesson, we're going to be talking about the third isomorphism theorem. This theorem answers the question of what happens when we take a quotient group of a quotient group. The answer? Nothing much. Here it shows that if we take the quotient group GH and take the quotient group of the quotient group by KH, notice the same H here and here, we find this is isomorphic to GK. So essentially, we can simplify out the H so that it never existed in the first place. The structure here and the structure here are the same. The addition of H, the quotienting by H, did not change that. Let's get started with the statement and the proof. The statement goes as follows. Let G be a group. Let H and K be two normal subgroups of G, with H being a subgroup of K. Then the first result says that H is a normal subgroup of K. The second result says that the quotient group of KH is a normal subgroup of the quotient group GH. And the third result is the isomorphism itself. So, the thing I want to comment on here, before getting into the proof, that if you see the first and second results, these two are preliminary results for the third results, just the same way we had preliminary results in the last lesson, the second isomorphism theorem. So here, to have a quotient group, we need the denominator of the quotient group to be a normal subgroup of the numerator of the quotient group. So do we have that? Well, on the right-hand side, we have that because K is supposed to be the normal subgroup of G. On the left-hand side, we have to have that KH is a normal subgroup of GH. And that is in fact what we're going to prove here. But also that H has to be a normal subgroup of G, but that is quite alright because we've supposed that is true. And that H is a normal subgroup of K. So this is what we need to prove as well. Let's get down to the proof. The proof of the first two parts of the proposition is fairly easier and more straightforward than the third. So the first part we have H is a normal subgroup of K. We already know it's a subgroup, so that all that's left is for us to show that H is closed under conjugates. So we let an element H in H and K in K. We want to show that the conjugate of H by K is an element in H. And this is in fact true because H is a normal subgroup of G. And since H is a normal subgroup of G and that K, which is an element in K, is contained inside G, so K is an element in G, so H is a normal subgroup in G, so it's closed under conjugates by definition of normal subgroup. This means that this is true and that H is a normal subgroup of K. In fact, this is true in general. If H is a normal subgroup of the entire group G, then it is of course a normal subgroup of any subgroup that lies inside G. Number two, we have that the quotient group KH is a normal subgroup of the quotient group GH. The proof is done similarly. Let the coset KH be an element in KH and the coset GH be an element in GH. We want to prove that the conjugate of KH by GH is an element in KH. So this is equal to GH, KH, G inverse H, because the inverse of the coset is equal to the coset of the inverse element, and this, by coset multiplication, equals GK, G inverse H. Now, we want this element to be an element in KH. The only way that is possible is if this element is an element in K. Is that true? Yes, it is true. This is an element in K because K is a normal subgroup of G. Since it's a normal subgroup, it is closed under conjugates. So any conjugate like this has to be also an element in K. And we have completed the proof of the first two parts of this theorem. To prove the third part of the theorem, I'll give you a bit of a spoiler here. We're going to be using the first theorem to prove the third theorem. The first theorem, recall, it is if you take a group G and you take the quotient of G by the kernel of phi, you find that this is isomorphic to the image of phi for some homomorphism phi. So the trick here is to get to that point where you can use the first isomorphism theorem. We need to somehow relate the statement we want to prove with the result that we have. And the way to do that is associating, you look here that G slash H can take the place of the group G. K slash H can take the place of kernel of phi, and G slash K hopefully takes the place of the image of phi. And we will construct our homomorphism phi on that basis. So we consider phi to take an element from the group GH and sends it to the group which is GK. And we want to see that phi is defined in a natural way. So phi will send an element from GH, but an element in GH looks like a coset, it's GH. And it sends to an element in GK, which is a coset GK. So this is the definition of phi. Now we would like to see that phi is a well-defined homomorphism that is surjective and that the kernel of phi is equal to K slash H. First thing, phi is well-defined. This is because if we have two cosets which are equal, this means that by definition of equal cosets that G2 inverse G1 is an element in H. But if G2 inverse G1 is an element in H, since H is a subgroup of K, well, of course, this element has to be an element in K as well. G2 inverse G1 is an element in K, and therefore we can use the same sort of argument to say G1K is equal to G2K. But G1K is the image of GH by phi. So this is phi of G1H. And G2K is the image of G2H by phi. And we have just successfully said that if two elements are equal in the domain, then their images are equal. Thereby, phi is well defined. Next, we want to prove that phi is a homomorphism. This is a fairly straightforward calculation. We take phi of the product of two elements, G1H and G2H, and this is equal to phi of the product of these, which is G1, G2H. And now we use the definition of phi, which, remember, takes a GH, gives a GK. So this is G1, G2K, and this by coset multiplication equals G1K, G2K, and this equals to phi of G1H times phi of G2H. We have successfully split up the phi of the elements, therefore phi is a homomorphism. Thirdly, we want to prove that phi is surjective. By proving this, we will have said that the image of phi is equal to the entirety of the codomain, which is G slash K. The reason it's surjective is because if we take any element in G slash K, we want to see that it's the image of some element. So take L to be an element in G slash K. Because it's an element in G slash K, then L is equal to G times K for some G in G. This is for some G in G. But GK is just the image of GH by phi. And this, of course, is an element in the image of phi, thereby saying that phi is surjective, proving that the image is exactly equal to GK. The last thing is to study what the kernel of phi looks like. We hope to see that the kernel of phi is exactly equal to k/h. Now, what happens if we study an element in the kernel of phi? GH being an element in ker phi. This is true if and only if you apply phi of GH, you get back the identity. What does the identity look like in G/K? Remember, G/K is the set of cosets, and the identity coset is just 1K or K. Looking at the left-hand side, we use the definition of phi to say this is equal to GK, and the right-hand side is still K. But now GK is equal to K means that G is an element in K. So if G is an element in K, that means that the coset GH has to be an element in K/H. So we've just successfully said that GH is in the kernel if and only if it is in K/H. That means that this set is equal to that set, meaning that ker phi is exactly equal to K/H. So we have just completed all of our necessary criteria in using the first isomorphism theorem. So by the first isomorphism theorem, we have that if we take the group G/H, and you quotient it with the kernel, which here is K/H, this is isomorphic to the image of phi, which is proven to be G/K. And that is exactly the third and final part of the proof of this theorem. To make the idea of the third theorem of isomorphism clearer, we're going to be using an example, and I'll give you a nice intuition at the end. So for the example, we have the group of integers, the additive group Z, and the two subgroups 6Z and 2Z. Recall that 6Z is the multiples of 6. So 6 times k for all integers k. And that is a subgroup of Z. But not only is it a subgroup, it's also a normal subgroup. And the reason is because Z is an abelian group. It's commutative. So all the subgroups are normal. And 2Z, similarly, it's all the multiples of 2, all the even numbers, and that also is a normal subgroup of Z. Now, what does GK, GH, and KH? Now, notice that H is a normal subgroup of Z, K is a normal subgroup of Z. The only thing left for us is to verify that H is a subgroup of K. And that is indeed the case because, first of all, every multiple of 6 is a multiple of 2. Obviously, every multiple of 6 is an even number, so H is a subgroup of K. Now we have all of the conditions to satisfy the third isomorphism theorem. The first result being that H is a normal subgroup of K. That is the first thing. And now because it's a normal subgroup, we can define the quotient group KH. GK and GH are already well defined. They're Z2Z and Z6Z respectively. But KH now is going to be 2Z quotiented on 6Z. Let us see what each of these quotient groups look like. Z2Z, of course, is the quotient group of two elements, 0 and 1. Z6Z is the quotient group of 6 elements, 0, 1, 2, 3, 4, and 5. Now, to understand what 2Z, 6Z looks like, we need to go back a bit and see how we constructed Z6Z. In Z6Z, we asked ourselves, what happens if I go through the integers and I collapse them modulo 6? So I went through all of the integers, I collapsed them modulo 6, and I got this. In 2Z6Z, I do not go through all of the integers. I only go through the even integers. So things like 1, 3, and 5 are not counted because they're not even. The only things that are counted are 0, 2, and 4. So this only gives me the classes 0, 2, and 4 modulo 6. Only 3 elements instead of 6. So now we can use the third isomorphism theorem to say that GH quotiented with KH is isomorphic to GK. So this entire group here, quotiented both by 6Z on both sides, is simply the cyclic group of two elements. Let me give you an intuition on that now. Now, I understand. If this feels like black sorcery, I get it. I also felt the same way when I first had this class. But let's trace back the steps and write this down explicitly so we know how this isomorphism is possible. To do that, recall that Z6Z is the 6 elements 0, 1, 2, 3, 4, 5. And 2Z6Z is simply 0, 2, and 4. Now recall, when we want to take the quotient group, what we do is we take an element here and we operate on all of the set here, all of the subgroup here. So this is how it's going to look like. First, we take the element 0, and then we're going to operate it, but the operation is addition, so we're going to add it to all the set 0, 2, 4. And I repeat the same thing with 1, 2, 3, 4, and 5. I'm going to list down all of the elements now. Okay, as you can see, I've listed all of the elements in the quotient group here. Let's now do some calculation in order to simplify how this quotient group looks like. So if you add 0 to any element here, it's not going to change anything. It's just going to be 0, 2, 4. If you add 1 to all of the elements, you're going to get 1, 3, and 5. What happens with the other elements? Let's see. If we add 2, we get 2, 4, and 6. But remember, we're dealing modulo 6 here. So modulo 6, 6 bar becomes 0 bar. Because the division, when you divide 6 by 6, we get a remainder of 0. So let's do the same with 3. We get 3, 5, and 7. But 7 bar is equal to 1 bar modulo 6 because 7 divided by 6 gives a remainder of 1. If we add 4 to all of the elements, we get 4, 6, and 8. But using the same logic, we get that this is 0 and that this is 2 bar. And lastly, we get that 5, 7, and 9. But here again, 5 is 5, 7 is 1, and 9 is 3. So, did you notice something here? These are all the same set. So they can all be represented by 0 bar, 2 bar, 4 bar. And on the other hand, these are the same set as well. So they can all be represented by 1 bar, 3 bar, and 5 bar. And now this set contains nothing but two elements, 0, 2, and 4, 1, 3, and 5. These are the even elements, these are the odd elements. So we can say they're isomorphic to 0 bar, even elements, and 1 bar, odd elements. This is Z to Z. You see how collapsing twice gave us Z to Z? So in fact, this here changed nothing. We simply had Z to Z back the way it was before. Putting the 6Z in both Z and 2Z did not change the structure of this quotient group. It gave us the exact same structure. I hope that this intuition has helped you shape your perspective on this nice theorem. If you did, drop a like, subscribe, and share with anyone who would be interested in this. I'll be dropping more content on group theory soon. Have a nice day, and bye.